Perfect. So welcome everybody. That's the last global Poisson meeting for this year 2023. We already know that after the new year, we come back on January 25th. Of course, you're gonna all get messages about it with the title and abstract and the speaker. Well, today we are very happy to have Sarah Scherotzke, who's going to speak on Calabi structures on bisymplectic algebras. So, Sarah, the floor is yours.
Thank you. So thank you very much for the invitation to the seminar. And so I will, like Anton said, I will talk about Calabi structures on bisymplectic algebras. So this is a joint project with Tristan Bozec and Damien Calaque. And can be found on the archive and is also already published under exactly that title. Let me give you as a motivation, what do we plan to do today? So in non-commutative, on the non-commutative algebra side, we will look at objects which are associative K algebras. During this whole talk, K will be a field of characteristic 0. And we're going to be interested in the following structures. So the quasi, I put quasi in brackets because I probably won't have time to go to the quasi case, but it's extremely, it's analogous to the bisymplectic case. And also, one can also consider, which is actually dual, the quasi double Poisson structures. So why were these structures invented? So the motivation is that in non-commutative algebra, we wanted to give a structure which in algebraic geometry corresponds to a structure which we already know. So on the algebraic geometry side, what we can do is we can associate to every associative K algebra a moduli space of representations. So I will just denote it with a V, and V is a finite dimensional vector space. Over K. And here we have a notion that is the notion of quasi Hamiltonian GL space.
Sarah, sorry to interrupt, but just maybe to understand. So this is something like Vandenberg, right? Or
yes, yeah. I was going to say that in a second. So
okay.
this here is goes back to, this is a structure which was invented. So the double Poisson by Vandenberg, and also goes back to Crawley-Bovey, Ettinghoff, and Ginzburg. And on the side, sorry, we also have the quasi-Poisson. Poisson GLN spaces. And these were invented, I think, also by you, Alexei, so Anton, Malik, and Meinreinken. So the connection is the following. So in algebraic geometry, we have these structures, and we can already find them on the, there are corresponding non-commutative structures on the side of the associative algebra, which will, if we take the representation space, so if we go over and take the representation space, we obtain our known GLn Hamiltonian spaces or Poisson GLN spaces. Okay, and these give rise on this side via symplectic reduction, or Hamiltonian reduction, I should rather say. Well, we obtain here Lagrangian maps. So of the form, yeah, from, for instance, in the case of a quasi Hamiltonian space, we'd obtain a Lagrangian map of this form going to the stack of representations, of GLN representations of the moduli space. So this is the classical picture. The picture that I'm more familiar with is the, so this is maybe, yeah, classical picture. And we want to compare this picture now with the picture in higher algebra. So in higher algebra, we have a very similar table in which on one side we have something, we have non-commutative analogs to commutative analogs, to geometrical invariants. So here we have K-linear DG categories. So these are differential graded categories. On the other side, we have objects in derived algebraic geometry. So what is it on the object? So if I can look more generally, instead of looking just at an associative K algebra, I can look at a smooth at a DG category. I will explain later exactly what a DG category is. And to such a DG category, by a theory of Toen and Vezzosi, I can associate very generally, analogously to the representation, to the representations of an algebra, I can look at the moduli spec of perfect objects of that DG category. Of any DG category A, really. Now the structure, the non-commutative structure that we will be interested on this side is the so-called Calabi structures. So in the absolute sense, so we have, we can say that DG category is Calabi. So I will define what this means. Or we can also say that a functor between DG categories is Calabi or relative Calabi. So in an absolute or in a relative sense. Okay, and this corresponds on the other side to shifted symplectic structures. In the absolute sense, and to Lagrangian maps if you look at relative Calabi structures. Morphisms. So we can define what a shifted Lagrangian morphism is between derived stacks. Okay, so here also, I mean, we also obtained a Lagrangian map, but from actually a quasi or a bisymplectic structure on a non-commutative algebra side. So the question is, what is the connection between these two pictures? And that's, let me maybe say also the references. So this goes back to the definition of the moduli stack of objects was given generally by Toen and Vezzosi. And the proof that Calabi structures give rise to, via the moduli stack constructions, to shifted symplectic structures was given by Braff and Dickerhoff. And the very definition of shifted symplectic structures goes back to a paper of Toen, Vaquier, Vezzosi, Toen, Vaquier, Vezzosi, and Pantev. Okay, so this is a quite recent development. And so how can we summarize this? So we have here what I can say, higher algebra. On the DG category side, we have the Calabi structure. So I will shorten Calabi with CK. On the non-commutative side, algebra side, we have bisymplectic structures. And both of them can be related in derived algebraic geometry more generally. So say derived or in algebraic geometry to symplectic structures. Okay, once by taking the representation space and the other time by taking the moduli stack of objects. And now what we will be concerned with today is to find a direct connection between these two bubbles. So we want to know, can I find a way to go from here to here such that I get a commutativity of these structures? Okay, and that's the goal of today. So that's today. So as a motivation, we will have this picture in mind, but today we will clarify what the connection is between Calabi structures on DG categories and bisymplectic structures on associative algebras, such that both of them give rise to the same symplectic structure once I go over to the moduli stack or the moduli space of representations. Okay, so yeah, that's the question of today. Is what is the connection between relative Calabi structures on DG categories and bisymplectic structures on associative algebras? Okay, so structure of the talk is the following. So in the first part, I will define what bisymplectic structures are. In the second part, I will define what Calabi structures are. And then we will clarify the connection. So we will establish the connection between the two. And the fourth part will be concrete applications in derived algebraic geometry. And actually, we wrote the whole paper. I mean, it's for bisymplectic structures, but they're actually dual to double Poisson structures. So everything that I say for bisymplectic structures is also valid for non-degenerate double Poisson structures. And we also solved the problem if you put quasi everywhere. So from quasi bisymplectic structures, the connection between quasi bisymplectic structures and Calabi structure. But I mean, because it's quite analogous, I mean, the quasi-symplectic case is just technically more difficult. I will focus on the bisymplectic case first. Okay, so let me give you the definition. So we let R be the following algebraic. It's the direct sum of idempotents. The EI are orthogonal idempotents, and one is the sum of all the EIs. Okay, so we want A to be, sorry, not curly A, just a normal A. Should be an associative R algebra. Okay, so now the first thing we want to introduce is what are in this context differential forms. A is not a commutative algebra, so we need to come up with some definition. And they're defined in this context in the following way. So the one forms of A are defined to be the kernel of the map, the multiplication map. So A tensor A over R to A. This is just the multiplication map. So these are called, so is the A bimodule of differential forms. Okay, we can now define, make a complex out of this. So we take the tensor algebra over the one forms as A bimodule. And as differential, there's a natural differential D, which is induced. So D is induced. So it's a -1 shift missing here by the map that maps A to omega R A1A and to the canonical differential form A tensor 1 minus 1 tensor A, which of course is in the kernel of the multiplication map. And we will denote this for this reason as, of course, as the image D of A. Okay, another definition is the definition of the derivatives. So we're gonna consider the double derivatives over R. So derivatives from A to A tensor A. And this is just the isomorphic to the Hom dual of the differential forms seen as A bimodule. Okay, I'm sorry, there's a lot of notation because, I mean, we're in a non-commutative case, so we need to set up what all this, what are differential forms in this case. And now we can define what a bisymplectic structure is. So we call A omega, so omega is a two form. Bisymplectic if it satisfies two properties, so B1 and B2. The first one is called closeness, so omega is closed. And also in this context, it's a little different. So it means also that the derivative of D is 0, but modulo the commutator is equal to 0 in the space in the complex of differential forms modulo the commutator brackets. Okay, and B2 is what is called non-degenerate. And here a two form gives rise to a morphism iota of omega between the derivatives and the differential forms. And we want this to be an isomorphism.
Maybe one question about terminology. Why bisymplectic? To me, it looks like pretty much symplectic.
I don't know how they came up with the terminology. I mean, yeah, to me as well, I must say. I mean, I think they call double or bi everything that happens on the non-commutative side. And I cannot exactly tell you where the terminology comes from.
Yeah, because otherwise, like
it's also two form, and I mean it's also closed, and and you also have a non-degenerate condition. Yeah. So it's really very similar to the symplectic Yeah, I don't know. I don't know actually. I didn't see any comment on that terminology. Yeah, I mean sometimes they say double, sometimes bi, but I mean for me it's also a little yeah, I couldn't tell you why actually.
Okay, thank you.
And then we have also a moment map. So you can actually always find a moment map. So it's not really a condition. So no, I mean, there's of course a condition, but you can always find a moment map to if you have a bisymplectic form. And we call mu. So mu consists actually of pairs mu ei. These are the ei's that are also indexed from 1 to n, like the idempotents. And mu I is an element in EI, A, EI. So remember, these are the idempotents that we defined R with. A moment map of the structure A omega if the differential of mu I is equal to iota of EI. So iota is the map that you get from a two form, here. So applied to omega for all I and EI. So EI is a differential form from A to, is double derivative, sorry. That sends A to AEI, tensor EI, minus EI, A, tensor EI. Okay, so let me, so the dual, let me maybe make just a remark. I didn't define what double Poisson was, but this notion, let me just say, this is a dual notion. Notion to, that was shown, I think, by Van den Berg, to non-degenerate double Poisson. So there's a one-to-one bijection between bisymplectic structures and non-degenerate double Poisson structures. But I mean, obviously, I'm not just going to define all these different structures, otherwise I would never finish. Let me give you a class of examples, and it's totally sufficient to just consider the problem also for bisymplectic structures. So class of examples, which is very important in this context, is the following. So you can you take a quiver, a finite quiver. So you want it to have a finite set of vertices and a finite set of edges. This set of vertices as usual. This is the set of edges. Both of them are finite sets. And we consider it's the double quiver. The double quiver. So it means it just has the same set of vertices, and for every and the set of edges, we just double every edge. For every edge alpha, we introduce an edge in the opposite direction. So let me say is alpha star, where alpha is an E and alpha star goes in the opposite direction. Okay, and now we can consider the following algebra, the path algebra of the double quiver. Okay, so for A2, that would be KA2, the following path algebra, two vertices, alpha and alpha star, and no commutativity relation. So yeah, it's an infinite dimensional algebra. Okay, so, and here we have the following Poisson structure. Sorry, not Poisson. We have the following bisymplectic structure. So these algebras are always bisymplectic. And here we can choose as omega the sum of dA star, where A just runs to all the edges of the original quiver. And we have a moment map, and the moment map is the following. Mu is given as the sum of the k of xi to A. Yeah, so I give it as a map from kxi. So the image, if you want the image mu I, what I denoted, I can write it down, yeah. Xi goes to the sum of all the commutators from A, between A and A star, where we run through all the A's which start in E. So t to the minus 1 of E, so it means a starting point is vertex E.
Excuse me, may I interrupt for a second?
Yeah, go ahead, yeah.
Should we think of this moment map as a moment map for some matrix group or something else?
For some matrix group?
Ordinarily, one thinks of a moment map as the moment map for some group acting on your symplectic manifold.
Yes,
Is there a group hiding here somewhere?
Yeah, I mean, in the it is a bit easier to see on the quasi-symplectic side, and the quasi-symplectic. So here also wanted to say that E runs to the vertices of the quiver. And once you go over to the geometric side, actually, you will go over to GLN. Actually, it will become a map in the opposite direction from the representation space into GLN. Actually, so it will be a moment map in the algebraic geometry sense. So in the Lie group, actually. So yeah, that is why we call it a moment map. So in representation of beforehand, mu I is the image of mu of xi, of course. Huh? So it is actually an element that lies in a EI, where this is the path of length 1.
Sorry, maybe one more stupid question. I kind of maybe missed it. So how is it the quiver? Is it oriented or?
It's an oriented quiver, yeah. Finite oriented quiver.
Okay, so
I
now
couldn't have defined T and S, so that's the starting and the terminal point. So to every edge, there's a map that goes from E to I. So that's maybe a better way to say it. And then you see it's oriented. So you have the terminal and the point where the arrow starts and the point where the arrow ends. And so here, for the moment map, you take the sum over all, at that point here, you take the sum over all arrows that terminate, terminate in I. So in a certain vertex I. So you take, so for instance, in that example here, you would take, you would send x1 to alpha times alpha star. And x2 you would send to alpha star alpha.
Sorry, but then I'm a little bit confused about the formula. Shouldn't we also take the terms which correspond to edges which start at I? You don't have in the moment map the term which would give you, I kind of, okay, maybe probably you're right, but if you think of the representation varieties there, wouldn't it be more like A star for the terms which whatever maybe end at I and A star A for
So this was also not correct. I mean, here you take the commutator. So, no, but if you did, yeah. So no, it's correct.
Yeah.
I thought this was correct. I can double check. I mean, you think we should yeah. I guess the difference is if we take well, we want these elements to be in AI. We want this to be paths that start in I and end in I, because they need to be in here.
But the commutator is not such a path, right? Because if you A and A star.
No, you lose the other part actually. Yeah, you will just the question is, do I have to go through all the arrows of E or also the arrows of E star?
I mean,
that's what you mean,
yeah. I think you need whatever some A star terms and some A star A terms.
Yeah.
Could be for two
that-
different conditions, but
Yeah,
let's say that's my memory, but maybe I'm wrong.
No, maybe I have to double check. I'm not entirely sure, but here you can just add, you just take all the errors of E. So you can define, yeah, you could, yeah, I will double check. Then you would have to add the A star A, and you have, and then you want A to be starting in I. Right, then A star would be terminating in E. Yeah, the other point, I will double check with the definition. The thing is, the question is, do I have to run through all the errors of A, of E, of both of the E and E star? I will double check, okay? Because now that you tell me, I'm not, I mean, for the A2 example, there is no choice. I mean, you can only take alpha, alpha star. This is the only path that ends and start in one. And the same for this here. So it doesn't make any difference. But usually if you have an arrow that would go in the other direction, indeed. So yeah, let me check. Let me check after the talk. I'll check this.
Okay, thank you.
Okay, because it's true. I'm not 100% sure. No, I think you're right, actually, because for the pre-projective algebra, these are the relations you want, and the pre-projective algebra will be a quotient of this. So yeah, I think these are the right relations. I also need to go to take the double errors into account as if they were errors of the original quiver. Yeah. Yeah. Okay, so that would be the moment map here in this case. Yeah, so we always get a bisymplectic structure with a moment map in this way. And it's not difficult to check that it's bisymplectic. Let me see. So in the let's talk now about Calabi structures, and I will give a very similar example, and I will already give you a hint to how the connection between the two structures is going to work. So Calabi structures on the G categories. And we will, I mean, in this talk, well, K is always a field of characteristic 0. Let A be a smooth algebra, a smooth DG category. So do you know what a DG category is? I mean, a DG category, you know what a category is? A K-linear category. So a K-linear category is a category which has objects, and its morphism spaces between objects are K-vector spaces. And in this case, in a DG category case, the vector space, the morphism spaces are actually complexes of vector spaces. So that's why we say differential graded categories. So in our case, we will always, actually, it will turn out that what will be relevant for us, but I'll give the general definition, are actually only K-linear categories. So whose home space is really a vector space, so only concentrated in degree 0 and not actually a complex. What does it mean to be smooth? So smooth is a technical condition. So smooth means, in this case, homologically smooth. So it means that A is a perfect A bimodule. So as in algebras, we can define what a module of a DG category is, and we can say that, and we can view every algebra as a bimodule over itself. We can do the same thing for DG categories completely analogously. And in fact, I invite you to just, if you don't know exactly, or you don't feel comfortable with DG categories, just think of a K-linear, just think of an associative algebra. An associative algebra, you can view as a category with one object, and the morphism spaces of that one object is the algebra itself. So that would be an algebra, a DG category that is a K-linear category concentrated in degree 0 with one object. So every associative algebra is also in particular a DG category. So this is what smooth means. So it's just a technical condition. And we will define also what the dualizing complex is. So V is the here we need to always work in the derived context. So it is the dual of, in the category of A bimodules, of A seen as an A bimodule. Okay, so this is an element that lives in the modules of A tensor A op. Okay, so this is really completely analogously. If I had said that A is an algebra, you would know everything that I'm writing down here. So you think just of A as an algebra. So this is called the inverse dualizing complex. And the R means that we look at the derived setting. So we're gonna take a resolution of A as an A bimodule, and then we can compute this complex explicitly. Okay, then we have the we will denote. So if A is smooth, we denote HH star of A. That's the Hochschild homology ring, and that's defined as A tensored with itself as an A bimodule. And because we are in the smooth context, this can be shown to be exactly the same thing than the derived Hom space between the inverse dualizing complex and A, both seen as A bimodules. Okay, so this is where we need the smoothness condition, or where it will appear later on. We denote, so that's the Hochschild homology of A. There's a cyclic refinement. I mean, now it's getting a little technical. So we have
Sorry. So that's the full Hochschild homology, or just Hochschild homology degree 1?
That's Hochschild. Sorry, that's Hochschild homology.
Mm-hmm. Okay.
No, it's not in degree 1 because we take we take derived here.
Okay.
So we take derived, so we're viewing it as a complex actually. So we take the whole complex. We consider the whole complex. Then we have HC star of A, which is negative cyclic homology. And we always have a forgetful functor. So negative cyclic homology you obtain, it's a bit technical because you have an S1 action on Hochschild homology and you can look at the homotopy fixed points. But you always have a forgetful functor to the Hochschild homology complex of A. And now I can define what it means to be Calabi-Yau. So definition. So the first in the in the absolute case, so an n Calabi-Yau structure a DG, a smooth DG category, a eta with eta is a class of degree n in negative cyclic homology. So another way to say it, it's to say it's a map between from K n, so shifted by n, to the complex negative cyclic homology in A, such that the underlying class, so that's a class in Hochschild homology, or we can also say rather it's a map from Kn to the Hochschild homology complex, is non-degenerate. So what does it mean? So it means, remember we said before, and Hochschild homology can also be viewed, because we're in a smooth context, as, so a class in Hochschild homology can be seen as a functor from the inverse dualizing complex into A. And non-degenerate means that eta defines an isomorphism of A bimodules. So eta seen, the forget full thing between the inverse dualizing complex shifted by n and A as A tensor A op modules. So every class in Hochschild homology will induce such a map or functor between this DG between this DG modules. And if this is actually an isomorphism, we say that we have an n-Calabi-Yau structure. So this is the relative notion. And unfortunately, for this talk, we do need the relative notion, which is slightly more involved and was also recently, quite recently invented. So, so we say that an n-Calabi-Yau structure on a cospan. What is a cospan? So cospan is the following. We have DG functors f, a DG functor f from A to C and DG functor G from B to C. So sorry, an n-Calabi-Yau structure on the cospan of all smooth DG categories. So is the following data. So it's, first of all, is a homotopy commutative diagram. So of the following kind. So we associate to every, we have a map CB, which goes from Kn into negative cyclic homology of B. So it will give me a class of degree n in negative cyclic homology. We get a class Ca of the negative cyclic homology of A. Now by functoriality, we always have, so negative cyclic homology is covariant. So we always get maps into the negative cyclic homology of the middle part, so C. So this is induced by G, by the map G, and this is induced by the map F. And we want this to be a homotopy commutative diagram. I mean, we want the structure will be given by the data of a homotopy commutative diagram. So we have a homotopy here that makes this diagram here commute. Maybe call it gamma. So in derived, I mean, in this higher algebra context, this is actually the choice of a class, a negative cyclic homology of C of degree n+1.
Sorry, so CA and CB are two classes, right?
Exactly, there are two classes in negative cyclic homology of A and negative cyclic homology of B, and we want the diagram to commute. So they should be mapped by F and G to the same class in negative cyclic homology of C. I mean, this is what it means in non-homotopy language. We would, I mean, now we have to see everything up to homotopy, but in non-homotopy language, we would say, okay, we have to choose a class in negative cyclic homology of C such that this diagram commutes. But here we actually have the choice of a homotopy such that this diagram commutes. So there is some extra data hidden here in the commutativity assumption. And then we also want, so what I will call Calabi-Yau 1 condition. No, this is the Calabi-Yau 1 condition. It's the homotopy commutativity of this diagram. So the data of this homotopy, and such that the choices of CA and CB are not just arbitrary. So CA and CB themselves have to be non-degenerate. So they actually induce Calabi-Yau structures on A and B. So CA and CB are non-degenerate in the sense that we defined above, are non-degenerate. So let me make a remark. So remark in particular that already implies that A with CA and B with the choice of CB are n-Calabi-Yau. As in part of the definition 1. And such that furthermore, we also want the following. So the inverse dualizing complex, you can consider the inverse dualizing complex of the category C shifted by n. Now taking the inverse dualizing complex is contravariant. So the map G will induce a map into the inverse dualizing complex shifted by n of B, seen as a C bimodule. So to tensor it up, which I know because of the Calabi-Yau structure, being non-degenerate, is isomorphic to B, also here tensored up, as a C bimodule, so seen as a C bimodule. So this is the isomorphism. This is given by the non-degenerate condition. We have the same thing on the other side. So we have contravariant map into the inverse dualizing complex of A. So A tensor A up, C tensor C up, which is isomorphic via CA, because we have a Calabi-Yau structure on A and B to A itself, seen here again as a C bimodule. And now we can use that, of course, we can just use the maps F and G, and they will induce maps back into C. So we get a square, and this square, the commutativity of the square is actually already implemented by Calabi-Yau once. We know the square is commutative. But we will ask the square to be Cartesian, and that will be my Calabi-Yau condition. So this is my Calabi-Yau condition 2. And Calabi-Yau condition 3 is, this is a Cartesian square. So in the category of C bimodules. So it means it's a push out and a pullback square at the same time. So it's not only commutative, it's also Cartesian. Okay, so that's yeah, I know that's quite a if you haven't seen that definition, it is the technical. Now let's maybe see some examples, and then we can see why we even think it could be related with bisymplectic structures. Of course, the terminology is very similar. We also have yeah, hidden closeness assumptions, non-degenerate assumptions, and so on. So let's see easy examples. So yeah, the example, of course, K itself is 0 Calabi-Yau. K of X together with the element in Hochschild homology, 1 tensor X is 1 Calabi-Yau. Yeah, so actually, the other way to see this is you also know that spec of K of X is A1, and A1 is 1 Calabi-Yau. So the notion, of course, of defining this Calabi-Yau structures also come from algebraic geometry. So of course, we also want it to be, yeah, if AN is n Calabi-Yau as a, I mean, in the sense of algebraic geometry, then of course K of X1 to Xn, the polynomial ring in n variables, is n Calabi-Yau. Okay, so now to the relative Calabi-Yau structures, we have that if I take the direct sum of K of Xi, so the co-product of the K of Xi, I going to all the vertices of the quiver Q, I take the same notation as before, and then I define a map into KQ, into KQ dual. So that's the path algebra we considered beforehand, sending Xi into the same sum. So sum of E commutated with E star, E in T to the minus 1 of I. And here I will again have to check because I might have done the same mistake of not taking the other commutators. E in S to the minus 1 of E. Call this map also mu. Then on this side here, because this is just a co-product of things that I know are one Calabi. I know this is one Calabi. And now I can consider a cospan, where here I just send to the empty DG category. And then one can check very easily that this is actually, I mean, very easily, I mean, not now, but we know that this is actually is a relative, is a one Calabi-Yau cospan. With homotopy, so we need to find a homotopy between mu of the sum of the one tensor xi. So these are the Calabi-Yau structures on the left-hand side, and 0 given by a class in Hochschild homology of degree 2. So one tensor A star minus one tensor A star tensor A, and here we sum over all A and E. This is an element in K2 maps to Hochschild homology of KQ, which gives me the homotopy. So this gives me the Calabi-Yau condition, and then you can the homotopy in condition 1, and then one can check that condition 2 and 3 with this choice are satisfied. Okay, so then of course, I mean, the idea is now that we want to compare. I mean, this moment map is basically the same than we've seen in the bisymplectic case for the same algebra. So the idea is to connect it's not difficult to get, so connect one Calabi-Yau cospans so of the form direct sum of the coproduct of the xi into a category C. On the other side, the empty set with bisymplectic structures on AC. And I will have to say, what is AC? So where AC is the following algebra. So AC. So I've talked about how we can view an associative algebra as DG category. Now we can also go the other way around. We can also, if we have a DG category with finitely many objects, then we can produce usually a DG algebra. But under certain hypotheses, we will produce an associative algebra out of it. So where AC is the following algebra, it's the sum over all the objects of C and well, pairs, let's say, I comma j, pairs of objects of C. And here we take all the Hom spaces between C and J. So, and we will assume that the objects of C are finite. And C is a K-linear category. Okay, and then indeed, AC is an associative algebra. R algebra, where R is K of the sum of the K of EIs, with the I run through the object of C. And the EIs are just the identity morphisms from I to I. So indeed, they are all orthogonal idempotents. Okay, and so in this way, I can go the other way around. I can produce out of a K-linear DG category finitely many objects. I can produce an algebra, and what we suspect is that relative Calabi-Yau cospans of the form above give rise to bisymplectic structures on AC with moment map mu, which goes from sum of K of Xi to AC. And here we take exactly the same, the picture, I mean, just the map. Let's call this F. So the Xi, yeah, so this will induce, let's call this mu, then it has the same notation. And then you see that this map mu, the moment map mu is just induced. So this guy is nothing else but A of the category K of Xi. Okay, so that's how the connection between the two works. So let me formulate this as a theorem. So let product of the Kxi to C be a relative. Of course, it always has to be one Calabi-Yau because K of Xi is one Calabi-Yau. So the relative Calabi-Yau structures is determined by the Calabi-Yau structures on the two outside parts. So in this case, yeah, we have a one Calabi-Yau structure. Liao functor such that, and we have one assumption, omega 1r of AC is projective as a bimodule. That's our one assumption that we cannot drop. And then AC is bisymplectic. And a mu sum of K of Xi to AC, the induced map, is the moment map. So, so let me just say theorem 2 is the same just for bisymplectic. So here you have to, for quasi-symplectic, so we have to change to introduce, yeah, yes?
Sorry, and what is the symplectic form?
The symplectic form, yeah, yeah, it's not, I can tell you, so that's the proof actually. Let me, so yeah, that goes into the proof. The proof works as follows. What we do is we have to compare negative cyclic homology. So the proof, so the structure, the Calabi-Yau structure on the side, the relative Calabi-Yau structure is induced by a class A negative cyclic homology of degree 2 of C. And so what we do is, so sketch, can say sketch, is we compare a negative cyclic homology, let's say a very specific realization of it, you can compute it in different ways. So you have to cleverly prove, I mean, get the right complex. So HC, so we have negative cyclic homology of C with the following complex. So you take the RAM form, differential forms on A, and you can compare it. I mean, if you have to add a variable u, and you have that the differential is then given by the map iota A that I have mentioned at the beginning minus UD. And we always have a map from here to the complex that computes negative cyclic homology. I'm not going to explain now in detail what all these operators are, B minus UB. So this one computes negative cyclic homology. And you always have a map between these two. So if you start here with the class that induces, let's say this is gamma that induces the relative Calabi-Yau structure on this functor, on the functor mu, then you can show that it's going to be mapped to a class omega, which induces, I mean, actually here we rather have a sum of omega I use, and it's omega 1 that is the one that where omega 1 induces the symplectic structure, the bisymplectic structure.
Sarah, maybe it's a good point to negotiate. How is it?
Yeah, indeed. I have I wanted to just I think there's one more thing I want to say, and then I can stop. Okay?
Yeah.
So maybe 5 more minutes, and then I'm done. So maybe the only thing I want to say, you can do exactly the same thing for a quasi bisymplectic. So and in this case, the only thing you have to modify is your moment map. It will go from a kxi plus minus. And then you get exactly the same theorem. And then maybe just to say, to go to the very beginning of my talk, I've been talking about this diagram, and that we wanted to close up the triangle. And maybe that's just the last remark. So we also prove that the symplectic reduction, that the triangle indeed commutes. So that the symplectic reductions on both sides give the same symplectic forms. So let's suppose we have in the theorem we have like a relative 1 Calabi-Yau structure. Let me just take the bisymplectic case now. So relative 1 Calabi-Yau structure, and then we know we can set A to be AC, so the path algebra of this category, and then we get a Lagrangian structure. So we can define XV, the representation space of AC with respect to a vector space that I fixed. So it's just the usual classical representation space. And now I have two ways of getting a symplectic structure. So the relative Calabi-Yau structure will by Brav-Dickerhoff induce the following, we get a Lagrangian structure, so a relative between the representation space modulo GLV and GLV modulo GLV. This is Lagrangian. So this is one way to get a Lagrangian structure. And the other way is now, what you can do is you have mu, you look at the bisymplectic structure on AC, and the bisymplectic structure can also get here from bisymplectic structure. So the bisymplectic structure on AC will induce a GLn Hamiltonian structure on XV, which will induce by Hamiltonian reduction a Lagrangian map of that kind. And then what we can show is that indeed these two Lagrangian structures are the same. So the Lagrangian structures. So if I go from the relative Calabi-Yau structure, I get my bisymplectic structure, and I induce the Lagrangian structure in this way, then this all commutes. Lagrangian structures induced from the relative Calabi-Yau structure coincides with the one induced from the bisymplectic structure. So that's also something we can show. We can show the triangle commutes. Yeah, then, yeah, well, there's a last result, but yeah, that's maybe not, I mean, an important procedure to produce a new bisymplectic structure is called fusion. And what we can also show is we can give an interpretation of this. I mean, if you have two, for instance, you have two bisymplectic structures on two different algebras, then you can glue the algebra at an idempotent together, and you can create a new bisymplectic structure on this algebra. So this is very useful, for instance, for quivers. You can just consider the A2 quiver and bisymplectic structures on the A2 quiver, and then you glue whatever vertex you want together, and you get whatever quiver you want, and you get a new bisymplectic structure on that quiver. And this is a procedure called fusion. And what we can also show is that this fusion procedure on the Calabi side coincides with a push-out procedure on Calabi on the Calabi push-out that comes from topology. I mean, from actually the pair of pens. But I mean, that's another, yeah, we'll take another 15 minutes. So let me stop here. So yeah, so that's another result that is related to this. We can also show that this important procedure of fusion on the bisymplectic and double Poisson side coincides or is induced on the Calabi side by push-outs with certain very typical, I mean, very specific types of Calabi cospans. Okay, let me stop here.
Okay, thanks a lot. Okay, so any questions or comments? You can either directly unmute yourself or raise your electronic hand. I maybe have a slightly provocative question. So your results show how to construct bisymplectic structures starting from Calabi categories. Now, maybe just to understand, does it allow you to produce some new interesting examples that we didn't know before?
So far, actually, not, no. But we could only, we did produce a new Calabi structure on the multiplicative preprojective algebra. So we have a new version of the multiplicative preprojective algebra in another paper. And the question that was arising was, do the symplectic structures coincide with the ones that had been found beforehand? And that is a question we can now answer with this procedure. So we can actually compare them and say that they are the same that we have beforehand. We haven't used it so far in this context. We haven't produced a new Lagrangian structures in this way, but of course it's possible. I mean, it just wasn't, I mean, we just wanted to clarify the picture. So that was our main motivation. It wasn't so much into, but I mean, it should be used in this way, of course. And I think also one of the maybe more, I mean, what should also be done is, there's also by Pridham, there is a notion of shifted bisymplectic, and so one should also generalize this picture and show that maybe shifted bisymplectic structures are actually in general coming from relative Calabi structures, so not only in degree 0. So here I only did the degree 0 picture, but there should be a generalization also to that. But I mean, your answer is no. I haven't found any new Lagrangian structures so far using that procedure. Using this method, but it should be possible. I mean, it's actually quite difficult. I would say it's more difficult to find bisymplectic, especially quasi-bisymplectic structures are very difficult to find, while relative Calabi structures are a little easier to produce.
Maybe another question, maybe I haven't quite got it. So your results go from Calabi to bisymplectic. Is there any way to go back, or maybe
we don't think it's true actually, but we're not quite sure. I mean, this map that I in the sketch that I gave you, it went from negative cyclic homology into the non-commutative differential forms. It's probably not an isomorphism, and we also need conditions of one smoothness. So I don't think they're actually equivalent. I think relative Calabi structure give rise to bisymplectic structures, but I don't think that they're necessarily equivalent. Yeah, but I'm not sure. I'm not sure actually. Yeah.
But if you add some qualifiers, like you, as you said, if you put some extra conditions, is there hope to get equivalence?
Yeah, it could be true. Yeah, we have to still investigate that actually.
Okay.
Although I think Damien believes not, but I have to still ask him why exactly not. But yeah.
Okay, thanks a lot. Any other questions or comments? Look, if not, Sarah, thanks again for this great talk. Thank you.
Thank you for the invitation, and yeah, have a good weekend.
Yeah, so thank you everybody, and happy holidays. And we're gonna wait for you on Global Poisson in January.
Bye.
Anton. Bye, Sarah.
Bye-bye. Thank you. Bye-bye.